go ahead and just start recording over here for a second. So you will have a quiz on stacks, not today, but tomorrow or Friday in your lab section. It's going to be fairly generous because as far as quizzes go. And I'll go ahead and I'll tell you one of the questions right now, okay, or at least what the question will be, if not exact phrasing, which is, give me some use cases for stacks. What can you use stacks on? So that would be one of the questions, okay. So otherwise, the questions are the other questions on that are extremely straightforward, okay. So that's with stacks. I also posted some videos about queues yesterday. So go ahead and watch them. Queues are not required, by the way, for your homework or this quiz. Queues will come up later, but they get taught with stacks. They're not as useful for all the fun stuff that we're doing. But queues, so stacks are what? They're last in, first out, right? The last thing you put in is the first thing that comes out of a stack. Queues, on the other hand, they're first in, first out. Imagine a line, congratulations, you have a queue, right? Queues are, you get in the back of the line, you wait for your turn, and then you exit the front of the line. There's a couple ways to look at that, which is that basically you insert from the back and remove from the front is one way to look at it. Another way to look at it is the item that's been waiting the longest to be processed is the next item that's going to be processed, which is a bit of a more honestly abstract way of looking at it, but if you think about it, that's what it means. Like, the person who's at the front of the line is the person who's been waiting in line the longest, right? They've been waiting there the longest to be processed. So use cases for stacks are things like buffers, where basically we have to hold on to we've got items coming in, and we need to process them, right? And so we need a data structure to hold these items as they're processed. Now, a linked list would work just as well for this. In fact, it works perfectly well for this. But the queue is kind of like, but by saying that we want a queue here, we're being very specific about what we want, and also saying, since it's a queue, if we only use the queue methods, then we are ensuring that nobody cuts in line, essentially, right? With a list, you can potentially cut in line. Speaking of cutting in line, we'll eventually be moving on from queues. Oh, come on. That was anticlimactic. Okay. We'll be moving on from queues, Q-U-E-U-E, to priority queues later on in the semester when we go on to heaps, priority queues. And if you might guess, those are queues where people can cut in line. Essentially, they're data structures where where items are deemed some items are deemed a higher priority than others, and the queue restructures itself. And as we'll see, we can do that in log n time because of the way it's structured. Basically, it sorts itself according to priority of who gets started. But any time where basically people have to wait for stuff, queues are generally the fairest way to do it, as I explained in the videos. If we use a stack to basically order the things that are processed, then people can, if we're using a stack, for instance, instead of a print queue to print documents, right? Everybody's waiting in a queue to print their documents. If we use a stack, then that essentially means the newest person gets to cut in front of everybody in the line. And that kind of gets into this whole game theory thing where some people could realize, wait a second, I'll just print my document again so it goes to the front of the stack. So that I get printed first, and then people will continually get into a war of trying to print their document first, and that just doesn't end well. So a stack is generally not the way if you want to maintain order. It's generally if you want to go backwards. All right. The other thing I want to address, and I just have to set up the projector for this, is a question that was commonly asked about the maze question, which is how do I actually physically move through the maze? Okay. And the answer is you use the stack, you push onto the stack to move. So, 1 second. Okay. Amazing. Hey, it didn't crash. Wonders of wonders. Okay. Auxiliary HDMI. Okay. Okay, so the other question with the maze, and hopefully people are having a fun time with that, is that, right, people are like, okay, how do I move on to the stack? So there's a couple things that I also noticed from last night. You know, people are checking. First is directions. People were doing north, south, east, west, but they were getting north wrong because because just something that may have not been taught in 1068, the way the coordinate plane works in graphics. Okay, so this is the coordinate plane, right? Your traditional coordinate plane is this, is this grid, right? And you've got you've got x, positive y, right? Well, that's not the way it works in computer science. In computer science and computer graphics, we work in this quadrant over here, this bottom one over here. And so instead what we do is that we say, imagine that we've got a computer monitor. Imagine that we've got a screen. It even looked good, too. Seriously? What is with this room? All right. Imagine we've got a computer monitor. All right? We've got the x direction over here, and then we've got the y direction over here. Specifically, down is positive y. And x over here is positive x. So this location over here is 0, 0. This top left corner is 0, 0. The bottom in the bottom right corner. This bottom right, it's however big the screen is. So, for instance, if I were to tick these, 2, 3, 4, 5, 1, 2, 3, 4, 5, the location 3, 5, the pixel 3, 5 would be 1, 2, 3, x, and then 5 down, so it'd be over here. And that's positive. So, so that means if you want to go north, that means that north is negative from your perspective, from your current location. So if you want to check the square to the north of you, that's -1. Okay, that's -1 to go north. Okay, and this may seem confusing, but fortunately it maps out to the way you think of two-dimensional arrays, where basically the row above you, that's the row north of you. Okay, so so next thing is, how do I actually move? Well, again, I have this. The algorithm there I have is a while loop, right? We have this while loop, and what I say to do is, because I keep seeing this done wrong, I want to make sure you get this. Is that I say your cell current should be equal to your stack dot peak, right? You get your current location there, okay? And now how do I get the cell to the north of me, right? Well, that would be, current, as it turns out, does have what current row it is. So you can find out what the cell to the north of you is by saying row -1, right? And it would be in the same column. So it'd be current dot column -1, right? Oh, sorry, not mul. For the same one, you just keep the column the same. And fortunately for us, we have this. I've provided you with this handy-dandy array of cells. And this would give you the guy to the north of you. Okay? So that's as much as I want to. So let's go ahead and just ask ourselves a couple questions. So this is the guy directly to the north. So what would this be? Which cell would this be? South. All right. What about +1, and then what about what direction would this be? West. Yep, it's the column to the left, so that would be west. And this would be the column to the right, which is east. Yep. So now the other question I have for you, just to mix things up, what's that? We can't move diagonal in this, but assume we could. Northeast. That is northeast, right? So +1 and -1 allow us to get our combinations. Now, mind you, this is easy in the sense that we only have 4 cardinal directions, and we don't have to worry about 8 directions, which is nice. All right, so that's that. Now, next week, what we're going to be doing. So the maze you'll want to finish this week. I'll probably extend the amount of time there is on the triple cut assignment, on the encryption assignment, so that people have more time to work on that if they so choose. And again, I'll look at that as one of the possible avenues for getting more points on the exam. With next week, you'll be seeing more assignments that are going to be very interesting. We are going to tackle. You're going to actually have a choice of problems to choose what you want to do. One of which will be the 8 queens problem. Another one that you'll choose to do, you'll have the choice of doing, is the Knight's Tour problem. And then you'll probably be writing a Sudoku solver next week. But I hope to do a bunch of also in-class exercises on some things, so you get a feeling of how they work. And the interesting thing about that is that all those problems I mentioned, they all use the same algorithm. You just have to figure out how to apply it onto this particular problem. All right. So with that.